welcome to ESC Live. We are here at Fullabrook Down Wind Farm in beautiful North Devon. You can see the amazing views all around us with some of these fantastic wind turbines in view. We're in between Barnstable and Ilfracombe over there. So hello to Ilfracombe Academy and Pilton Community College. I used to go to Pilton Community College many years ago, so hi everyone. So we're joined by some fantastic experts today who are going to help us understand a little bit more about how the wind can generate electricity and power things in your home. So yeah, we're at 800 feet above sea level at this really great site for wind. This site was built in 2012 by ESB, which is the Electricity Supply Board, and we've got Mark Jones with us today from the ESB, so that's be great to talk to him later. So we'll start with introductions. So I am Dr Alice Mills. I used to be an astrophysicist, and then I got really excited about science outreach and started wanting to tell people about science. And now I'm one of the founders and directors of the Exeter Science Centre, and we're a charity that's working to create a STEAM Discovery Centre in Exeter. Brill. So I work alongside Natalie here.
Hello, I'm Dr Natalie Whitehead, and I'm one of the founders and directors of Exeter Science Centre alongside Alice. I did a PhD in physics and an undergraduate degree in physics, and before that I was an engineer for 3 years making sustainable buildings in Southampton. That's me, and over to Mark.
Hello, so I'm Mark Jones. I'm the wind farm manager here at Fullabrook. I work for ESB. Prior to working for ESB, I was a vehicle technician, and then I kind of progressed into the wind industry. So that's me.
Hello everyone, I'm Dr Adam Feldman, and I'm a lecturer at the University of Exeter. I teach the subject of renewable energy engineering, but even though we're the University of Exeter, my department is the wing of the university that's down in Cornwall near to Falmouth, where we do all sorts of research into renewable energy, and we teach renewable energy to students as undergraduate students after school, as postgraduate students wanting to become real experts, and people going on to study doctorates in renewable energy, people who are making their whole life's career into this fantastic form of engineering.
Adam, can you tell us a little bit about wind energy?
Well, let's get talking about wind energy. And what is it? It's one of the renewable energies, an incredibly important form of renewable energy. It's actually a form of sunshine or solar energy because the wind is made by the sunshine. What the sunshine does is that it heats up the atmosphere, the air around us, and it heats it up to different levels at different sites around the globe of the Earth. And wherever you have a high pressure and a low pressure, you get a pressure difference, and the wind blows from one site to the other. So remember that wind energy is sunshine energy. Now, why is this so important? Why is renewable energy what we've all got to do? As you probably know, until recent times, we used the fossil fuels. This is oil, gas, coal, peat burning. And as a result, we released all sorts of pollutants into the atmosphere. And especially so, we released a lot of the gas you'll have heard about, carbon dioxide. And carbon dioxide keeps heat in the atmosphere, and the Earth is heating up. This is what global warming is all about. And unless we do something about this, we're all going to run into big problems. And this is where renewable energy comes in, because what renewable energy is, it's the types of energy that are replenishable as fast as we use them. And it doesn't release carbon dioxide into the atmosphere. Essentially, there are 7 varieties. 5 of them come from the sunshine. That's solar energy itself, wind energy, hydro energy, wave energy, and biomass energy from photosynthesis. And there's 2 other varieties that get their source of energy from a different origin. One of those is tidal energy, and some of you will know that's from gravity pulling the motion of the Earth and the Moon around the Earth in the seas. And the seventh variety of renewable energy is geothermal energy, which is due to the heat that's built into the rocks beneath us. But today is all about wind energy. And when I started in renewable energy around 20 years ago, only 2 to 3% of the United Kingdom's electricity came from wind energy. It had first been installed in the UK, very near to here, in the neighbouring bit of North Cornwall to Devon, and we made 2 to 3% of our electricity from wind. These days, last year, we made a quarter, 25% of all our electricity in the United Kingdom from wind energy. So at this point, I'm going to pass on to my colleagues as we start to explore this amazing subject.
Fantastic. So today you're going to be having the opportunity to ask your questions live to the experts. We're going to be finding out how you run a facility like this, who's involved, what kinds of engineering is involved in the designing and the building and the maintaining. And you'll get a chance in the middle to do a little challenge where you find out a bit more about why wind is so good at generating electricity. Fantastic. So first of all, we're going to have a little chat with Mark Jones over here.
Mark, you are very familiar with these wind turbines and this amazing site. And I suppose you can see, if you cast the camera down across the hillside there, we have an amazing array of wind turbines that this site covers. So how many are there, Mark?
So Fullabrook Wind Farm consists of 22 Vestas V90 turbines.
So 22 turbines, that's a huge amount. And how big are they? So I think we can pan up to this one that we're in front of right here. And how big is it? It feels pretty big from here.
Yeah, so the tower height up into the nacelle there is 65 metres.
Right.
And also we have a blade length there of 45 metres. So each blade is 45 metres long.
Goodness me, so the diameter is about 90 metres across there.
That's correct,
That's fantastic. And I think we're going to walk a little bit closer so you get a bit of a feel for the sound here. So it isn't actually that loud. It's quite, it's just a kind of gentle whooshing. I hope that's coming over on the microphones okay. So how much power do these generate, perhaps across the site and maybe each one as well?
So each wind turbine is 3 megawatt, so 3,000 kilowatt, which gives us a total capacity of 66 megawatt across the site here.
66 megawatts, and how many homes might that be?
So that can power up to 30,000 homes.
30,000. Something that I was really impressed about, so since we've been here on site, we've seen that this turbine's actually changing direction. So these must be really clever devices. Can you tell us a little bit about that?
Yeah, so the turbine is constantly monitoring the wind speed and the wind direction, and it's able to yaw the turbine into position and follow the best wind, really.
I think what we might just do is go a little bit closer so you can see and hear a little bit more from the turbine. How efficient would these turbines be? How much, and by efficiency we mean how much energy is getting converted into real work? So you might be, generating a theoretical amount of power, and then really because of losses and heat and sound, it isn't 100% efficient. So what is the efficiency of these?
The turbines, they run roughly between 30 and 40% efficiency, because you can imagine all the wind which is hitting the front of the blade.
Yes.
Some of it does pass through, which doesn't create that energy, and that's where we get our losses in wind.
And I suppose all of the kind of, how they move, and there's going to be some friction, and there's going to be
there's friction in the gearboxes. And
let's go and have a look inside, Mark. Maybe you can lead us in there. That would be great. We've had a lot of questions. Oh, maybe as we go up there, we can hear those, Alice. If you can.
Right, as we're going inside, I'll just check the first one. So, Ilfracombe Monty asks, why aren't there more windmills around Devon? There don't seem to be very many.
A good question, but a lot of that comes down to planning, really. There's a lot of work which goes into planning. It's not just a matter of somebody putting a planning application in and then suddenly the wind turbines start popping up. But you know, for me, I'd love to see more turbines in the area for sure.
Brill. And Mr. Hayes' class has asked, what are they made of?
What are they made of? So the towers are made of steel. You can see, you might be able to get a picture here of how thick the tower section is. Then the nacelles, they can differ between steel and they can also be fiberglass. The hubs themselves are made out of steel, and the blades are made out of fiberglass and balsa wood.
Fantastic, thank you. So what can we see in there?
Yeah. So I'll just talk you around briefly what we have inside. So here we have a lift. Now the lift is there for the technicians to ascend the turbines and descend the turbines during maintenance. If the lift is out of order, or if there is a power cut to the turbine due to a power failure, maybe on the grid or an issue, they also have a ladder system which they can use to ascend and descend. Here we have the high voltage switchgear. So this is what's providing the power to the nacelle. That comes in at 33,000 volts and then climbs up this cable, the red cable there, up to the transformer upstairs, where that gets turned down to 690 volt.
The thing that I'm surprised about is how high voltage that is. So 33,000 volts, and that gets converted and sent off to the national grid. Is that right?
That's right. Yeah. But it gets stepped up down at the substation again, up to 132,000 volt onto the grid.
Wowie. So, okay, and that's in a separate transformer which is down off-site. So you have to take these cables all the way underneath the turbine, I suppose, and under the ground
and then
over there.
under the ground down to the substation, yeah.
Right, it's a lot of electricity. So perhaps if we pop down as well, and we'll move out of here. So if you're into electronics and electrical engineering, there's loads of roles in engineering in that sense, and also making these amazing structures as well. A lot of structural engineering that goes into that too.
Cool. So, yeah, want to just learn a bit more about what's involved in this site. So just really quickly, if we could sort of, what's your role, Mark, when you're here? What's your day-to-day job?
So I'm responsible for the day-to-day running of site, really, any health and safety concerns. I'm also here to look after the high voltage network. So if there's any high voltage servicing which is required on the turbines, which we do annually, then it's my responsibility to make that system safe for the guys to work on. I'm responsible for the substation. Again, that's ensuring safety from the system for guys to work on it annually, and just any day-to-day issues, really.
Is there, all these turbines are sitting on this beautiful green space, which is much nicer than a big old power station sitting, taking up loads of room. What can you use the land for around it? So
the land can be utilised by usually farmers, we lease the land off them, and they carry on using all the land around it as they normally would, so they can grow crops. You can see that they've got sheep here, there's cows on other parts of it as well, so it's basically usable as it was before, apart from the footprint that you can see here now.
We've had a couple of questions. Have there been any problems with them damaging wildlife or killing birds, for example?
I've been in the industry for 12 years now, and I've never seen anything to suggest it. I mean, I can't say that it doesn't happen. There are surveys which go on. I've seen it on a number of sites where they'll come around and do surveys on maybe bats and birds and stuff like that, but I've never seen anything myself personally.
That's good. That's good to hear. Brilliant. So yeah, we're going to go into your challenge now. So Adam's going to very quickly introduce the challenge that you've got to do, and maybe we'll just give you 5 minutes to do it. So thanks, Adam.
Hi again, everyone. I've got the most amazing challenge for you. Something that I'd like you as a class to decide. The question is, what is the mass? How many kilograms or tons, or whatever unit you want to use, of air blowing through the blades of this wind turbine? Us engineers, we make tiny things sometimes that you can't even see with the naked eye. And at the other end of the scale, we make the biggest machines that you can imagine. And these days, wind turbines are the single largest moving man-made machine that we've ever come up with. So when you try to think of your answer as to how many kilograms of air every 1 second are blowing through this turbine, I want you to bear in mind that the blades are 90 metres diameter. 90 metres diameter. And just so you can imagine that, some of you will have run down an 100-metre sprint track on sports day. That's quite a long way, and that is the size of these blades. What you should do is try to work out how massive, how many grams or kilograms 1 cubic metre of air is. Look under the desk you're probably sitting at. That's probably about 1 metre cubed. How heavy is that air under there? And then work out in 1 second, when the wind is blowing at about 10, 11 metres per second, how many metres cubed of air are blowing through those blades. And in that way, you might be able to make a really good estimate. And a lot of engineering is all about estimation. It's all about making a good educated guess. So have a little guess, work out how massive 1 metre cubed of air is and how many metre cubed might be blowing through some of those turbines that we see in the distance every second. Hi everyone. Has anybody got an idea yet of what the mass of air going through the blades of the turbine every second are?
We've had the Year 8 Pilton saying 1,500 kilograms.
1,500 kilograms from Pilton.
Pilton, Year 8.
And so that's 1,500, that's 1.5 tons of air. Yep, we'll have a look at that in a minute. Thank you for that answer.
We have Ilfracombe, who've guessed between 60 and 1,000 kilograms. That's quite a range. And one person says they think it would be much higher, a ridiculous number. So
I like that one, the ridiculous number. That's fantastic. Well, let's have a look at things, because what I've struggled up the hill with is the most important part, probably, of the wind turbine in this box. Let's have a look inside it. There it is. The most important part of the wind turbine is air. Now then, let's consider this air, why it's so important, why these machines can make the electricity for 30,000 homes, which is what, 120,000 people, the population of North Devon being supplied by electricity just from this wind farm. That's potty. Well, let's have a consideration. Let's look at this first panel, and I'll try and stand out of the shadow. These are Vestas V90 wind turbines. They make all sorts of turbines of different diameters, but these are V90s, 90 metres, almost the length of that 100-metre running track. Now, when the wind is blowing on a sort of average 11 metres per second, which is 40 kilometres an hour or 25 miles per hour, each turbine here generates 3 megawatts of electricity. That is 3 million joules a second. And I've brought a little analogy along. I've brought my apple, which shows us what 1 joule of energy is that you'll learn about. One apple weighing 100 grams, 1 Newton force, falling 1 metre, gives us 1 joule of energy. So let's bear that in mind. Each of these turbines, 3 megawatts, 3 million apples falling a metre per second. Now, the air. What's air made of? Well, 78% nitrogen, 21% oxygen, 1% argon, and then there's little bits of the other rare noble gases, helium, neon, krypton, xenon, radon, and only a titchy-witchy bit of carbon dioxide, 0.04%, but it's that 0.04% that does all the trouble with global warming. Now, let's move on. When you go in, probably you haven't learnt about moles yet in your chemistry and physics, but you may have done. And it's the way we work out how heavy the quantity of any particular chemical is. And what we use is that big table that I'm sure you've got on the wall of your science lab, the periodic table that tells us atomic numbers and atomic masses. And if we have a look back at our table of gases, nitrogen has an atomic mass of 14, or N2, the molecule 28, and oxygen 32, and so on. And from that, in a year or two, as you develop your science, you'll work out that you can tell what 1 mole, what's one certain quantity of those gases weigh. And you'll also discover that on a nice day like today, 20 degrees centigrade and 1 atmosphere pressure, each mole of that gas will occupy a volume of 24 litres. It shrinks down a bit in cold weather, actually. It becomes a little bit more dense in the winter. And that's what these panels talk about. We'll pass this information to your teachers so you can go through it in more detail. But what this does tell us is that 1 mole of any gas occupies 24 litres. Therefore, 1 metre cubed of air, the air under the desk that you're probably sitting at, we can work out will weigh 1.2 kilograms. I bet you wouldn't have guessed that. It has a mass of 1.2 kilograms. In winter, it has a mass of 1.3 kilograms because it's colder. So the next thing we have to do on these turbines is consider their size. How much air blows through there at 11 metres per second? Well, we work out the area, the circle, the swept area of those blades. 45 metres radius. We use pi r squared. I'm sure you've done that in maths. I've got pi to 100 decimal places on my shirt so I don't forget its value. And we say 45 squared times pi, and the area of the swept area of these turbines is 6,500 metres cubed. And when the wind is blowing at 11 metres a second, a cylinder 11 metres long will blow through those blades. So if we multiply that area, 6,500 by 11, we find out that we have 70,000 metres cubed of air in 1 second going through the turbine blades. And if each one of those metres cubed, as we calculated from the chemistry, weighs 1.2, has a mass of 1.2 kilograms, we find that 1.2 times 70,000 gives us 84,000 kilograms a second. 84 tonnes of air. 84 small family motor cars every second driving through those blades at 25 miles an hour. And that's where the wind energy comes from. And if we take the next bit of physics that you'll have heard of, we can work out how much kinetic energy that is, half mv squared. We can feed in our 84 tonnes, 84,000 kilograms, multiply it by a half, multiply it by the speed of the air, 11 metres squared, and we find out that the power, the number of joules going through per second those blades is 5,082,000. 5,082,000 apples, I want you to imagine, all falling 1 metre every second going through those blades. We call that 5.1 megawatts. Mega means a million. But actually, as my colleagues earlier on said, it's not totally efficient. We have an inefficiency. We can't capture all of that energy. Something the very most interested mathematicians in your class, I want you to ponder the fact that if all the air gave up its kinetic energy as it went through the blades, it would come to a standstill behind the blades, and it would be like a traffic jam, and it would stop. And there was a man in Germany called Betz who calculated this, and he showed that it was possible to still clear the air behind any kind of spinning turbine machine, but still extract 60% of the energy, 59.3%. You can find online really enthusiastic mathematicians to tell you how and why this happens. And this is called the Betz limit. So 60% is the highest possible. But just before I stop here, I just want to make you all become engineers, because these machines are huge next to me. I said they're 90 metres diameter, the length of your running track, 84 tonnes a second going through the blades, giving us 3 megawatts of electrical power, huge amount of electricity. But actually, these are small turbines for today, because out at sea, we are building even bigger turbines. For example, the Siemens Gamesa, but also Vestas, are building turbines to make 15 megawatts. And they've got blades 222 metres diameter. Can you imagine that? Moving. They've been built by engineers who were once school children, who were once university students, who built these machines, and they last at sea. And 222 metre blades, 11 metres a second, going through their blades are 510 tonnes a second of this valuable air blowing through. 510 motor cars a second. So that is where the power of these wind turbines comes from. And we can build them. You can build them.
That is incredible. Thank you so much, Adam. That's an amazing description. So actually, some people did get pretty close. Mr. Goodland's class at 76,000 kilos, they get.
Yes.
And Miss Gavin's 82,000 kilos. So some fantastic calculating there. Amazing. So just really quickly, can you run us through how these things up in the top there, up in that nacelle, how
Let's
are these
run
things?
up to
let's
the-
run up here.
run up
how are
to
these
the
things
machines. We've got
actually
some models.
generating electricity?
Yes. So the reason I got into wind turbines and renewable energy was a long time ago. I was just on my old job driving through the countryside, and they were building some of these wind turbines, smaller ones than this, 15, 20 years ago. But I was amazed when I saw the bits on the floor and realised how huge that nacelle, that box at the top of the turbine is going. And here we have a model wind turbine going round. And even the tower is a high-tech piece of a kit, how it stays up. Remember, there's 80 tonnes a second going smashing into that machine, and it's not falling over. So even that's a high-tech piece of kit. But what we have up at the top is the hub, the blades. We have a gearbox to speed up the turn of the blades and to drive a generator. We have kit that controls, puts the turbine back to face the wind. This one's done by a tail, but these ones do it by having a weather vane and monitoring, and electrically. We call the turning into the wind yawing. It's a bit like in a boat, Y-A-W, yawing into the wind. We have a device to turn the pitch of the blades. I'm going to alter the pitch of the blades here to make them slightly less angled, and I'm going to put that up, and it's not going round. So what I'm going to do is I'll change the pitch of the blades to match the wind, and off it goes. And there's a device, the anemometer, measuring the wind on the nacelle up there, detecting the wind speed and adjusting the pitch of all those blades. And then there's all the electrical conditioning equipment that turns the power that's being made in the generator, the electricity, into a suitable form to pump into the grid, to get to your school, to get to your house, so that it matches it perfectly. It's what we call an alternating current. It has to wobble up and down. It isn't a direct current out of like in a battery. So that's what we have up there. But some other little models here. How does the generator work? Well, I've got a little model here to show how. We have a coil of wire here and a magnet. You can see that needle on a magnet. And if we connect some electricity to, I'll just get it running, there you go. Wherever you have an electric current flowing, you get a magnetic field. And this is why a motor works, because the electricity through the coil of wire reacts with the magnetic field on the outside here. And every energy machine goes forwards and backwards. And if I was to spin this coil by hand rather than drive it, I would generate an electrical current. And just as a quick, we haven't got long, just as a quick pointing out, the turbine up the top there has a gearbox in it to speed up. My hand is doing what the turbine blades are doing, and then the gearbox speeds up that turn, which then drives the generator, which then generates electricity. If anybody gave a little pull on that, we'd actually see it generating. Yeah, thanks very much. We might see it. Yes, if we go in carefully on the lights from the top. I'm just tensioning up the pulley system of the gearbox. And there we have a model of what's going on inside that nacelle.
So Mr. Hayes' class, and actually Miss Gavin's class as well, wanted to know how much does each one cost, because they're very keen to put one on Pilsen Community College, apparently.
Right, so a rough rule of thumb is £1 million a megawatt. Now that may have changed recently, but that's a rule of thumb that we always used to work to. So one of these machines, you're looking at £3 million.
However, a good calculation to do at some point would be to work out how much energy your school actually uses, because it won't need one this size. So, okay, what other questions have we got? How many wind turbines would make the same amount of energy as a standard coal-fired power station? That's from Miss Gavin's class. Any ideas? That's putting you on the spot there.
Okay, the largest coal-fired power station in the United Kingdom is called the Drax Power Station. It's recently partially gone over to burning wood to make it a bit more ecological, but it was built as a 3 gigawatt, that's 3 times 10 to the 9, or 3,000 megawatt coal-fired power station. That's the largest one in Britain. So that is equivalent to 1,000 of these 3 megawatt turbines, 3 gigawatts. But most coal-fired power stations are about 1 gigawatt. The average nuclear power station is almost a gigawatt. It's about 800 megawatts. And a typical gas-fired power station is about 700 to 1,000 megawatts. It's 0.7 to 1 gigawatt. So you can work out how many 3 megawatt machines you need. If you go offshore, where the wind turbines are turning to 10 to 15 megawatts, to make a gigawatt, you only need 100 of them. And wind energy is now the cheapest way of generating electricity in the world.
Fantastic, thank you so much. I think we've got one more for you, Mark. Owen at Ilfracombe would like to know what happens if there's a fire due to a malfunction. So, basically, what can go wrong, and what do you do if something does go wrong?
So if we have any issues on the turbine, if we were to have a fire, for instance, in a turbine, which is very rare these days, back probably 15, 20 years ago, it might have been a bit more common, but it's definitely not so common anymore. Our electrical systems will kind of shut themselves down. Any cooling fans on cabinets shut themselves off, so we're not introducing any air into the system, which kind of fuels the fire. Some turbines are fitted with fire suppression devices as well, which if they detect a fire, it will the fire extinguisher will go off and extinguish anything in the turbine.
Brilliant, thank you. Actually, one little one left for you. What is the lifespan of Fullabrook? How much longer is this all going to last? It was built in 2012, is that right?
Yeah. So 20 years originally. You can extend the life of the wind farm, so you can put an application in to extend it for another 5 years. I know of some wind farms up around my local area that are getting nearer to the 30-year mark now. It just means that there's a lot of inspections which need to happen to ensure the kind of integrity of the whole system before they get signed off to continue to operate.
Fantastic, thank you so much. I think that's all we've got time for today. You've asked such brilliant questions, and what we'll do is we'll get the experts to answer them, and we'll send the spreadsheets of answers to your teachers so you can see your questions answered. Thank you so much, Pilton and Ilfracombe, for taking part, and for your brilliant answers to the challenge in the middle. Thank you so much to Dr Adam Feldman from the University of Exeter, to Mark Jones from ESB, and to everyone at the Exeter Science Centre team. Thank you for taking part, and goodbye!